Unit 2, question 2. Part A asks us to determine the indefinite integral e to the 2x sine 3x. The thing that you should try when you see something like this is the product rule, because there are two terms, and another thing is like when you see the product of an exponential with a trigonometric, a common technique to evaluate this is to use integration by parts twice. The reason is that differentiation and an integration leave the exponential unchanged. However, for sine, it'll convert it to cosine, and for cosine, it'll convert it to sine. So if you do it twice, for example, sine will convert to cosine, and then it'll convert right back to sine. So the idea is to do it twice, more or less. It's a common technique that you should be familiar with, right? So let's do it for this question. So we're going to do integration by parts. So integral e to the 2x sine 3x dx. If I let u equal e to the 2x and dv equals sine 3x dx, well then du, I know it's 2e to the 2x dx, and v is equal to cosine minus cosine of 3x over 3. So if I use my integration by parts formula, this thing is equal to minus e to the 2x cosine 3x over 3 minus the integral now of v du, and there's a minus sign here, so I'm just going to put a plus, and then the factor 2 over 3 here, e to the 2x cosine 3x dx. And remember, I'm just going to write this again, this is equal to the integral of e to the 2x sine 3x dx. So now what I'm going to do is I'm going to do integration by parts on this thing to get it back to being the sine. If I do that with u equal e to the 2x and dv equal cosine 3x, again du is 2e to the 2x dx, and v will be sine 3x over 3. So if I was to do that, writing back everything, e to the minus 2x cosine 3x over 3 plus 2 over 3. And now here it'll be uv, which is e to the 2x sine 3x over 3 minus integral of v du, which is now minus 2 over 3 integral e to the 2x sine 3x dx. And the left-hand side, I'm just going to copy it back. Is equals to integral e to the 2x sine 3x dx. Now I can actually solve it, because what I can do is I can just, these two things are the exact same thing, so I can basically solve for them in this equation. And if I do that by bringing that term to the right-hand side, I get, well, 2 over 3 times 2 over 3 is 4 over 9. And if I bring all that on the other side, I get 13 over 9 integral e to the 2x sine 3x dx is equal to 2 over 3 e to the 2x sine 3x, I guess 2 over 9, and then minus e to the 2x cosine 3x over 3, and then I'm just going to add plus c, and then of course the last step will be to multiply by 9 over 13, so I got integral e to the 2x sine 3x dx is equal to 2 over 13 e to the 2x sine 3x minus let's see, 3 over 13 e to the 2x cosine 3x plus another constant c. Part B asks us to use de Moivre's theorem to show that 1 plus 3i to the 4 is equal to 28 minus 96i. First thing we should do is we should recall what de Moivre's theorem says. De Moivre's theorem says if you have something like r times cosine theta plus I sine theta to the n, that's equal to r to the n times cosine n theta plus I sine of n theta. So the goal that we have to do, first step, is that we have to find what r and theta are. So to do that, I have to write 1 plus 3i is equal to r cosine theta plus I sine theta. So that means that r cosine theta has to equal 1 and r sine theta has to equal 3. And I'm going to solve these simultaneously. Let's call this 1 and let's call this 2. If I square them and add them, since cos squared plus sine squared is 1, I get that r squared is equal to 10 actually. So then r is equal to the square root of 10. And then since r cosine theta is equal to 1, that means that cosine theta is equal to 1 over square root 10. And that means that theta is equal to cos inverse 1 over square root 10, right? And if I was to do that, I get, let's see, cos inverse of 1 over square root 10. So in radians, it's 1.25. So I have my r and I have my theta, and now I'm raising it to the power of 4. So let's write that 1 plus 3i to the 4 is equal to square root 10 cosine 1.25 plus I sine 1.25 to the 4, which by De Moivre's theorem is this, equal to square root 10 to the 4 cosine 4 times 1.25 is 5 plus I sine 5. Remember this is in radians, and then, okay, so let's write here. It's good to say by De Moivre's theorem. It's good to state when you're using the theorem in your calculation. Square root 10 to the 4 is 100. And then what's cosine of 5? Cosine of 5 is 0.28 plus I times sine of 5. Oh, it's actually minus, minus I times 0.96, which is in fact 28 minus 96i. That's exactly what they asked us to show. Part C asks us to, it's a reduction formula question. These tend to be on the more difficult side for CAPE. One thing I'd suggest, like, let's say you try something like this and you end up like getting a bit stuck. It may not, it's sometimes a good idea to move on and make sure that you can get points on the questions that you do know how to do and then come back afterwards, rather than spending too much time on this question and then not having enough time to do the things that you could do and could get full points had you more time. And like, for example, the question following this, it's to use the reduction formula to show something, but you don't actually have to do part 1 to do part 2 because you have the formula. They give you the formula in part 1. So you don't have to do part 1, even if you just skip it, right? And generally, CAPE tends to be forgiving with stuff like that. They allow you to like do other parts without like doing the previous parts, right? Okay, having said that, now let's do this problem. It's the integral of sine to the nx dx. Reduction formula questions tend to be about integration by parts. And the difficulty is to figure out what to choose for your u and what to choose for your dv. One thing that can help is like making sure that whatever you choose u and dv to be, the product uv will have to be something of this form. So that could help guide you figure out, okay, well, the power of cosine x is 1. And the way I'm going to get cosine x, how am I going to get cosine x from this thing? And then try and think about it a little bit. Okay, so let's begin. Integral sine to the nx dx. I'm going to choose u equals sine to the n minus 1x. So then du is equal to n minus 1 sine to the n minus 2x times cosine x dx. And then v will have to be sine, dv, sorry, will have to be sine x dx. So that means if I just integrate, v is equal to minus cosine x. If I use integration by parts now, uv is going to be minus cosine x sine to the n minus 1x, and then minus integral v du, and then there's a minus sign for this v, so that becomes a plus. I can pull the n minus 1 factor out. It's n minus 1 integral sine to the n minus 2x cosine squared x dx. Unfortunately, this is not quite yet of the form that they're asking us to do. You have to apply some trigonometry, because I know that cosine squared x is 1 minus sine squared x. So I can just put this entire line back, and instead now I'm going to put 1 minus sine squared x here. Okay, and then if I expand this, what's going to happen is I'm going to get minus cosine x sine to the n minus 1 x plus n minus 1 integral sine to the n minus 2x dx, and then plus, oh, I guess minus actually, minus n minus 1 integral, well, sine to the n minus 2x times sine squared x is just sine to the nx dx. And again, this is not exactly what we wanted to show, but we have to realize that this integral here is exactly what's on the left-hand side. Because remember, the left-hand side is just this. That's the same thing. So if I was to pull that onto the left, if I was to pull this term onto the left-hand side, I'm going to get n minus 1 plus 1, which is just n integral sine to the n x dx is equal to minus cosine x sine to the n minus 1 x plus n minus 1 integral sine to the n minus 2x dx. And then the last step is simply divide by n, and I get integral sine to the nx dx is equal to minus cosine x sine n minus 1x over n plus n minus 1 over m integral sine to the n minus 2x dx. And that's the formula that I wanted to show. But keep in mind, like, this is quite difficult. There are a few things that you have to do. You have to be very conscious about doing. Like, when I see this cosine squared term, I can't just give up there. I have to realize, okay, well, cosine squared is 1 minus sine squared. Can I do anything with that? Okay, well, this term looks like one term that I want it to be, but what about the other term? And then you have to realize, oh, the other term is just the term on the left-hand side as well. All right, last part now. They're asking us to show that the integral of sine to the 6x is this expression, and we're going to use the formula. Let me just copy the formula down so that we have easy access to it. Now remember, this formula is true for any value of n, and it just has to be an integer. So I can let n be 6, for example. So that's the first thing I'm going to do. All right, integral sine 6x dx equals minus 1 over 6 sine to the 5x cosine x plus 5 over 6 integral sine to the 4x dx. That's just the formula with n equals 6. The next step I'm going to do is I'm going to just do the formula again, but with n equals 4, and put what I get there in place of this integral sine to the 4x. So I'm just copying this back because I see that that directly corresponds to that term right there, and then plus 5 over 6. Now with n equals 4, you get minus 1 over 4 sine cubed x cosine x plus, and now n is 4, so n minus 1 over n will just be 3 over 4 integral sine squared x dx. And then the last thing I have to do is I just have to expand the brackets and simplify a little bit. 5 over 6 times 1 over 4 is minus 5 over 24 sine cubed x cosine x, and then 5 over 6 times 3 over 4 is 5 over 8 integral sine squared x dx. And what do you know? That's exactly what they asked us to show.